First thing, remember we watched those videos about the scale of the universe? What was something that we remember about watching those videos? Yes, Jackson?
That the universe is not 100 billion light years.
It's very big. It's several hundred light years across. It's very, very big. What is something else that we might have learned about watching our scale of the universe video? That video that showed the different sizes. Did we learn something there? Blake?
Each Earth is bigger, or each planet was bigger.
There was a lot of planets that got a lot bigger, and then what else did we see that was much larger?
Universes?
Well, there's one big universe. What do we orbit around?
The sun,
And what is the sun?
I guess. Oh, stars.
They're stars, yes, they're stars. We saw a lot of different stars. Something we learned is that there are billions of stars throughout the universe, hundreds of billions of stars found in the universe. We classify those stars into several different categories. Now, the way that we make these categories is based off of the size of the star, based off of its mass, so how dense it is, and based off of its temperature, because its temperature is going to tell us what color it is. So we are also going to be looking at, again, our classifications of stars, and then we'll get into galaxies and we'll get into nebulas. And hopefully the pictures I've chosen are interesting enough. So starting with the stars. So first off, this is about our average life cycle of a star. Stars can become a couple of different things over the course of their lifetime. All stars begin in what we call a stellar nebula. A nebula is a collection of gas and cosmic dust that over time, the pressure combines those to form stars. Nebulas are what we call the cradles of new stars. They're the birthplace of these new stars. So from there, stars can become either massive stars or average stars. Then begins their life cycle. So an average star, as it burns through its fuel supply, it will then become a red giant. And as it slowly starts to die down, it can become a planetary nebula and a white dwarf. The planetary nebula has the white dwarf at its center, and all of the stuff around it is the particles that have come off from the fuel burning off of the star. Ben, you got a question?
What's the biggest star?
The biggest star, those are our supergiants. We're going to look at some pictures of supergiants in just a little bit. So we have our massive stars down here. Now our massive stars, similarly to our average stars, as they burn their fuel, they will expand and they will become supergiants. Now supergiants, when they burn through their fuel supplies, they will become so pressurized and so condensed that they will explode out into what we call a supernova. So a supernova has one of two things that it can become afterwards. It can become what we call a neutron star, or it could become a black hole. So it could become one of those two things, both highly super dense objects. Pablo.
Is a massive star actually massive?
Yes.
How big would it be?
Keep that thought in your mind, because we're going to get to there in just a moment, okay?
Also, why in the pictures the black hole not black? Why is it?
So this is, obviously this is not like a physical representation of what it would look like. This is an artistic representation, and they chose the blue and the white for contrast to be able to show you that the black hole's at the center.
Okay.
So our star, the sun, is what we refer to as a main sequence star. So these are the most popular, most populous stars in our universe. They make up about 90% of the universe's star population. Their main sources of fuel are a combination of helium and hydrogen, which will come into play in just a moment. These stars can range from about 1/10 the size of the sun's mass to about 200 times the mass of the sun. So they can be very, very small and very, very big. Our sun is pretty average in the range of main sequence stars. These stars can live for millions to billions of years, like our sun. This is a representation of the chart of stars. So our main sequence is going to be this line that runs down here. So all of the stars along this sequence, those are what we call our main sequence stars. Up here we have our supergiants, and then our giants, and then our white dwarfs will be down there. The way that we read this chart, not to get into it too much because a lot of that is something that you'll learn in high school or in college. We measure by temperature and we measure by size and luminosity. So depending on how luminous or how bright an object is and how hot it is, it goes up and down on the chart. So high brightness, low temperature. Have we ever looked at a fire, like a campfire? Yeah. So you know how the embers of like the wood from below, what color are those embers? You can call it out, Blake.
Orange.
They're orange. They're maybe a little bit more red in color, right? Are they giving off a lot of heat? Are they giving off a lot of light? The embers themselves. Like if you just looked at the coals in the bottom of the fire, are they giving off a lot of heat?
No.
A lot of light? No. So that is where these stars are going to be. They're going to not be giving off a lot of heat. They're not going to be giving off a lot of light. Now, when you look at an actual fire, it's typically what? Orange, yellow in color. So that is where that mid-range is. So this mid-range here, it's giving off a decent amount of heat, decent amount of light. Have we ever looked at the stove, at like a gas stove, and you looked at the flame there? What color can that flame be sometimes? Elizabeth? It could be blue. So the higher that a star goes, the color-wise, it's the hotter that it's going to be. So our hottest stars are going to be this white-blue color because that is how flame is. We judge the stars and we see their colors based off of the surface temperature of these stars. So kind of keep this chart in the back of your head as we are looking at other stars. And the sun is right there. So our main sequence stars, as they are consuming the hydrogen in their core, once they run out of that, they begin to expand because they need to take in other elements to be able to continue to stay fueled, to continue to stay alive. So a main sequence star becomes a red giant when it becomes about 8 times less than the mass of the sun, and then it runs out of the hydrogen at its core. So what happens is that the gravity increases and creates high pressure. So the core of the star is beginning to shrink, but the star itself is beginning to expand. So our sun, in about 5 billion years, is going to become a red giant. So its core is going to shrink, but it will expand over time. So it'll become much larger. Now, what that means for Earth and the solar system as a whole is the gravity won't really change super much. It won't change all too much, but what is going to happen is that the dimness, as the star gets dimmer, it's not going to be able to radiate the heat and the light as far. So our planet could become more, possibly, like Mars, what Mars is like now. But that is all more theoretical than it is not. So we looked at this we looked at this star in our Scale of the Universe video that we watched the other class. So this star is much bigger than the sun, if we remember. This is Arcturus, very, very bright star that you can see in the night sky. Highly recommend if you are interested in looking at stars or constellations to download a constellation app because it gives you so much information about what stars are in the constellation. They'll show you like the positioning and even the movement of certain stars and also lots of other things. They're pretty cool. But this is an artistic representation of the star. We don't actually have a good high quality image of Arcturus at this time. This is also an artistic representation of the red giant Aldebaran and the sun for comparison. So very, very big, very, very little. And this is just a red giant. This isn't even a supergiant. So there are stars that are even bigger than this. So after a red giant expends all of its energy at its core, what happens is that it becomes a white dwarf. So this is essentially the core remnant of that red giant. They are typically the size of the Earth. So even then, it is still very big in comparison to us. They're the size of the Earth, but they have hundreds, if not thousands, the mass of the Earth. So they are incredibly dense celestial objects. Because they are so small and because they have consumed most of their fuel, they do not give off any new heat and they begin to start cooling down. This is what the sun will become about 10 billion years from now. So about 5 billion years from now, it will become a red giant. And then 5 billion years after that, it will become a white dwarf. Now, the most well-known white dwarf that we have in our universe is known as Sirius B. So Sirius B is in the constellation Sirius. As you can see by this slightly pixelated image, it's about the same size as Earth. It's a little bit smaller than that of Earth. This is a photo of the two stars, Sirius A and Sirius B. This is Sirius A. This tiny little speck here is Sirius B. So Sirius A is a main sequence star. Sirius B is a tiny little white dwarf. As you can see, it's not really giving off a whole lot of light. Yes, Ben, we have a question. This is a real picture, yeah. Yeah. I believe, don't quote me on this, I don't know if this one got taken from the Hubble. I meant to, I have it sourced somewhere, but most of my images are going to come from NASA. Pablo.
Is there like more Siriuses or is it just A?
So Sirius A and B, they're named that because of the constellation that they are in and also by their proximity to one another. So other stars in the Sirius constellation might be named Sirius, but Sirius A and B are the two most well-known ones. So, kind of jumping ahead a little bit, but we have our neutron stars. Neutron stars are formed after a star goes supernova. So these stars have about 8 to 20 times the mass of the sun, but they lose their hydrogen at the core. And they will begin burning other elements to maintain and try and maintain their energy, try and maintain staying alive. What happens then is as that fuel burns up, they become so pressurized that they explode into a supernova. And what is left is one of two things. It is either a black hole or it is what we call a neutron star, this super dense remnant of a supernova. So we have the Crab Nebula. Now the Crab Nebula is what we call a supernova remnant. The star that was initially here exploded a long time ago, and this is what remains of it. It is hard to make out, but right in this area here is where the neutron star of the Crab Nebula is located. It's located right in this light area here. All this cloud, all this cosmic dust here is the remnants of the star that exploded. And this will begin a new birthplace for several more stars to come. This is how new stars get created. This image came from the Hubble. That I do know. This is another supernova remnant. This is in the Aquila constellation. As you can see here, you have all of that exploding out from the center. The neutron star is located somewhere in here. They're not easy to see because they don't give off a lot of light, because most of their fuel, most of their energy, their luminosity has been expended during the supernova. Yes, Jackson?
Was that last photo artistic?
No, that's an actual photo.
Oh, that was very
Yes. It's an actual photo taken by the Hubble. The way that the colors come up, it has to do with what wavelengths the cameras and telescopes are pointed in. So if we get to it, I do have a little slider that shows you what the Crab Nebula specifically will look like in visible light, X-ray, infrared. A lot of these equipment that NASA has and other scientists have, they have the ability to see other wavelengths that are not the visible light spectrum. So we talked about, when we talked about wavelengths, we talked about visible light specifically, but we have so many other types of wavelengths, and this equipment is able to send those wavelengths out and receive them back, and that is how we get these wonderfully bright, colorful images. Now, red dwarfs, these were the smallest on that main sequence. They were all the way in the bottom right. Tiny, tiny little stars. They are the smallest of the main sequence stars and the coolest in temperature. They can live for trillions of years because they consume their hydrogen at a slow, constant rate. So they're able to maintain themselves for a very, very long time. They make up about 75% of our own Milky Way. So a lot of the stars in our own Milky Way galaxy, 75% of them, so 3/4 of the stars in our Milky Way galaxy are made up of red dwarfs. Now our closest star neighbor and the most popular of the red dwarfs is Proxima Centauri. Proxima Centauri is, I think, approximately 4 light years away from us. So it's still quite a distance away, because if we remember, do we remember what the calculation for 1 light year was in miles? I wrote it down on the board, but it's one of those numbers that doesn't really stick with us unless we're using it a lot. 5.88 times 10 to the 12th miles. So 5.88 trillion miles times 4 away. So it's the closest to us, but it's still quite a ways away. This is a red dwarf. It doesn't give off a lot of light. It's not very big. This image was taken from the Hubble. And the reason why I know that was taken from the Hubble is because it has these 4 light flares. These 4 light spikes that jump out of it. The Hubble has 4 mirrors that allow it to position to angle to take the photos that it needs. And in doing so, it has these 4 points of light that emanate out from various stars. The James Webb Space Telescope, the other telescope up there, will point out 6 star points. So you'll see that. Take a notice in the images if you see 4, if you see 6, and then you'll know what telescope it's coming from.